we're back, and we're picking up where we left off before, which was, let's see, last time we proved that the determinant of a matrix is equal to the determinant of its transpose. That was property 1.41. This time we're going to pick up with property 1.42, and it's in the book by Shilov, it's referred to as the antisymmetry property. But here's what it says. Let A be a square matrix and let B be a matrix that is formed from A by interchanging two columns or rows. Then the determinant of A is equal to the negative of the determinant of B. In other words, you just change the sign. So when you switch rows in a matrix, how does that affect the determinant? Well, it switches the sign of the determinant. That's what it does. And it does it regardless of whether you're switching rows or columns. So here's the proof. Suppose B is formed from A by interchanging two rows of A. The determinant of A is given by this. And that's just the definition of the determinant. You should be familiar at least with that by now. Ideally, you'd be comfortable with it by now, but that's the definition. If you aren't, go ahead and watch one of the previous videos where I define the determinant. So anyways, interchanging rows of the determinant corresponds to transposing terms in the permutation alpha 1, alpha 2, alpha 3, all the way through alpha n. Right, because that's the definition of the determinant, really. Anyway, so as was mentioned in the section on permutations, any transposition can be written as some product of an odd number of adjacent transpositions. And every adjacent transposition changes the parity of the original permutation. Okay, so switching rows transposes terms in the permutation, which then in turn changes the parity, right, of the permutation, is the gist. Hence, transposing terms of alpha 1, alpha 2, blah, 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 changes the parity, as I said, and therefore changes the sign produced by negative 1 to that power, where n of alpha 1, alpha 2 through alpha n is the number of inversions. So we've changed the sign. So although determinant B will have the same terms as determinant A, corresponding terms will have opposite signs, making it the negative of the original determinant. Thus, the determinant of A is equal to negative determinant B when rows of A are interchanged. Okay, now how about the columns? Because that's the other part. Now suppose that B is formed from A by interchanging columns instead of rows. Well, here's a tricky move. We're going to use property 1.41. Then B transpose is the matrix that results from interchanging rows of A. Right? If B is formed by interchanging columns, then if I take B transpose, well, that's the matrix that's formed from interchanging rows. Right? I've interchanged rows instead now. Okay, and we have determinant of A is equal to the negative determinant of B transpose. And since interchanging rows changes the sign of the determinant, as we already proved. By property 1.41, however, the determinant of B is equal to the determinant of B transpose. How about that? Now, substitution yields determinant of A is equal to the negative of determinant of B transpose, which is equal to the negative of determinant of B. And thus, interchanging columns also changes the sign of the determinant. QED, we proved it. And that's done. But note, it should be noted that once property 1.42 was established for rows, it followed immediately for columns by property 1.41. Because of property 1.41, all the properties of determinants which apply to rows also apply to columns and vice versa. Although we will not mention it again, the viewer should remain conscious of this fact. So anytime we prove something for rows, it applies to columns, or if we prove it for columns, well, it applies to rows too by property 1.41. And that's the end of the video there. See you next time.